everybody to another YouTube discussion hour. I'm filling in for Ed today because he's under the weather. He's still with us. Today we have Ethan talking to us about some of his PhD work. Ethan is a fourth-year PhD student with Kirsten Becker and obviously audio and.
You know, the audio is terrible, by the way.
His bachelor's at University of Florida. He's worked on a bunch of different projects, and he's going to be talking to us about convergent and some of the fieldwork things.
Yeah, thanks, Anna. Thanks all for having me here. As she said, this project is on the Tectonic Geomorphology of Hispaniola. We're going to look at structural geology, geomorphology, as well as thermocronology to try to piece together how the island was constructed and explain the sense of it. This work, as Aaron said, was with Claudio Pacena, as well as Thorsten and Danny. We're all as a team advising. So yeah, let's go. So I thought it'd be nice to start with kind of an introduction into what tectonic geomorphology is, because many of us here might not be familiar, especially if we're coming from different fields. So it's basically a field of study that aims to understand topography as a function of tectonics and surface processes. I think these line drawings are very nice to illustrate this. So you have some fold structure in the subsurface, and the topography is really matching that fold structure. So where you have the A's or the anticlines, you have ridges, and where you have the dips, the U's, you have valleys. And so once we have an understanding of how topography responds to tectonics and surface processes, then we can go forward and use the topography to try to back out some information on the tectonics. So that's kind of our goal here, and then combining it with other tools to try to further the work. So our study question is based on oblique collision. So where you have a tectonic margin and it's a convergent margin, but you have some angle of obliquity to that margin. We're interested in how that margin evolves when you have changing obliquity or changing convergence rates or other like complications through time, and how that affects the evolution of strain localization at these oblique margins. We're going to focus on the Northern Caribbean plate boundary in Hispaniola. This is a large-scale transcurrent margin, so strike slip margin that accommodates about 2 centimeters per year of oblique convergence between the North American and Caribbean plates. We chose this boundary because it has all of those things that we're interested in. It has the varying convergence rates, varying obliquity, and we can piece together the history in Hispaniola and then try to learn something about how plate margins respond to these changing parameters. The boundary itself is characterized by 2 major events that are going to be important to remember throughout the talk. A late Eocene transition from compression to strike slip, so right around 50 million years ago, and then a mid to late Miocene accretion of kind of the southern terrains in Hispaniola, these Caribbean plate terrains. And why are we interested in this? So kind of motivating this talk is that it helps us understand earthquake and seismic hazard in Hispaniola. This is an active plate boundary. There's many destructive earthquakes, historical earthquakes. And then from more of a philosophical perspective, it helps us understand how landscapes evolve through time, through geologic time, and how we can expect landscapes to evolve in the future. So just stepping through a quick outline, we're going to start with, there's a lot of animation, so it's kind of, I have to click a lot. We're going to start with the tectonic overview, then go into the physiography or topography of Hispaniola. We're going to talk about the geology of Hispaniola, the structural geology, the geomorphology, thermocronology, and then a synthesis. So a lot of stuff's going to go into this. We're going to speed through it, but hopefully it will be fairly straightforward, and we'll end, of course, with a little bit of question and answer. So let's start with the tectonic overview. This map here shows the tectonic realm of the Caribbean. The numbers point out some major important tectonic features that we're interested in, but here we're going to just focus on the Northern Caribbean plate boundary, so up in the top of the screen here. To go through some of these, number 1 is the suture between between Cuba and North America. So Cuba was sutured onto the North American plate. It's now part of the North American plate. It's no longer part of the Caribbean plate. Number 2 is the Bahama platform. So this is a thick piece of oceanic crust that's they think has entered into the subduction trench and kind of jammed up the subduction zone and changed everything. And this is kind of what pushed that transition into late Eocene. 3 is a deformed belt just north of Hispaniola called the Northern Hispaniola Deformed Belt. 4 is an oceanic spreading center, the Cayman Trough, and that bounds the west side of 5 here, the Ganav microplate, and the northern portion of that microplate is one of our important faults here, accommodating that 2 centimeters per year of convergence, the Septentrional Oriente fault, and that dips down into Hispaniola where you see the number 9. And that bounds this small tectonic sliver called the Hispaniola sliver. 7 here on the southern portion of the Ganav microplate is the Enriquillo Plantain Garden Fault. And so that's going through Jamaica into southern Haiti and then into the Dominican Republic, and then kind of curving into the Muertos thrust, which might be a back thrust or might be a full-on subduction zone. It's hard to say. It's not very well imaged. On top of this, we have some GPS vectors from kind of different sources. So the blue, the cyan color, is going to be the GPS solution for individual GPS stations. So we can see those kind of scattered throughout Hispaniola. It's giving us an idea about how each of these pieces in Hispaniola are moving relative to each other. These green arrows are going to be the Morvell kind of global plate model, showing the convergence between North America and the Caribbean plate with a fixed Caribbean plate, effectively a fixed Caribbean plate, really. Yellow is going to show the trench motion of the Lesser Antilles, and then the SKS isn't really important within the scope of this talk, but that's going to give a good proxy for kind of mantle flow. So trying to understand how the Caribbean evolved, this is just a quick G-plates reconstruction showing that the Caribbean started somewhere around the Pacific or between the separating North and South America as Pangeo is breaking apart. And it's going to move to the northeast relative to North and South America. You see Cuba sutured onto the North American plate. You see this boundary become the left lateral strike slip plate boundary that we have today. And you see Hispaniola starting to piece together throughout the evolution of the boundary. You see the southern terrain accreting on. And these events are all going to be important when it comes to looking at the topography and the different components of uplift in Hispaniola. So piecing, so taking a few snapshots out of that, if we start at 60 million years ago, we see this ancient volcanic arc, the Great Arc of the Caribbean, that formed much of the material that we have in the Greater Antilles, those being Jamaica, Cuba, Hispaniola, and Puerto Rico. And on top of that, in the red dots, I've put the volcanic ages that have sort of been cut for each of these time periods. And so we have a little bit of a gap here between the Bahama platform that I pointed out earlier and this Great Arc of the Caribbean. But that's about to close, like I said, around 50 million years. And the Bahama platform supposedly enters the trench, jams up the subduction zone, and kind of everything shifts around. You have a reorganization of that boundary, and you start to initiate this large transcurrent plate margin. Hispaniola is kind of coming together, and you start to have volcanism in the Lesser Antilles. And 20 million years ago, you have something resembling what we have today. Of course, much changes. This is really shown up here when I've overlain geochronological magmatic ages over the Greater and Lesser Antilles. And you see this younging trend from around 100 million years in the Greater Antilles to much younger present-day volcanic and present-day magmatic ages in the Lesser Antilles, because you have active volcanism there. So things are happening now. But this is good evidence for kind of these two different subduction zones where you have the Great Arc, the older ages, and then the Lesser Antilles Arc, those younger ages. In kind of a different space, in longitude H space, so this is going across the Greater Antilles. In blue, you have Cuba, orange Jamaica, yellow Hispaniola. So you see that the magnetism on these islands ended around 50 million years, concurrent with the spreading of the Cayman Trough. Then if you move into Puerto Rico, the ages are a bit younger, but they more or less bridge those to the onset of volcanism in the Lesser Antilles. You have some younger ages here. Those aren't very well interpreted or explained, but the thoughts are either it comes from kind of crustal melting, just due to maybe at the active subduction zone, but it's uncertain. Okay, the physiography of Hispaniola. Here's a nice picture looking out from just south of the central mountain chain, looking out into the looking south towards the sea, towards the Caribbean. And this is just a topographic map of Hispaniola. So I'm going to point out the major mountain ranges that we're interested in, and then go through the corresponding kind of main valleys that we're going to talk about. The first one is the Cordillera Septentrional. The second is the Central Cordillera. The third is the Sierra de Neva. The fifth is the Sierra de Bajarroco. The fourth is the Cordillera Oriental. And then as far as the valleys, you have the Cibao Valley, the San Juan Valley, the Azua Valley, and the Enriquillo Valley. There's a lot of words there. I'm just going to repeat them as I go through and as I talk about them. But getting a general picture, you have this high mountain range in the center of the island. It has the highest point in the Caribbean, Pico Duarte, and you have some of these very deep valleys. So some of these are sub-sea level. The Enriquillo Valley is the lowest point in the Caribbean at around -60 meters. All right, stepping into the geology of Hispaniola, these next few slides, I'm going to step through different stages of the evolution, different time periods as Hispaniola evolves, starting in the Jurassic. And you'll see some colors that are going to be superimposed onto the digital elevation model, showing the geology that's related to that time period. And so if you see a color up here, it's going to be stacking on top of the older units, but you'll see a color up here that's associated with that time. And some you'll see sort of highlighted if you have continued deposition or volcanism in those places, for example. Let's skip the Jurassic. Starting in the Jurassic, you have kind of these lower crustal rocks, these mafic and ultramafic complexes, and as well as mafic schists and amphibolite facies, metamorphic rocks. And then going into the Cretaceous, this is really when you have the major period of arc activity, or the onset of major arc activity. In green here, we have the volcanic arc. You have little patches of the volcanic arc showing up throughout the island. The pink here is intruding the volcanic arc. These are mostly tonalitic compositions, so kind of granitoid batholiths that are intruding the arc. And then up here in the Cordillera Septentrional, you have some accretionary prism rocks that have been exhumed after the collision. All right, moving into the Paleocene, you sort of have more of the same, more granitoid intrusives, more accretionary prism rocks, and more volcanism and magnetism. And then the Eocene is an important time in Hispaniola, because you have the onset of clastic deposition in this basin here, the Ocoa Basin, just to the south of the Central Cordillera. And that's important because that's depositing on top of erosional unconformity that's marking the transition in Hispaniola. So that's kind of our evidence for the transition in Hispaniola, is the onset of clastic sedimentation in this basin. You have clastics deposited in the northern portion of the island as well. And then stepping into the Oligocene, you have continued clastic sedimentary rocks forming in the Ocoa Basin and in other basins to the south of the Central Cordillera, as well as in the north. And then in the Miocene, you start to have the progradation of a clastic wedge out of these basins. And importantly, this is when the island has been exposed above sea level. So you have continental clastic rocks. So as everything is starting to be uplifted, you have this clastic sedimentation sort of prograding out of here, synchronous with that uplift. And then finally, in the Pliocene, and then we can just even step into Quaternary, you have these superficial deposits, some of these reefal deposits, and then you even have, as I mentioned, those volcanic rocks that showed up in the earlier plot. All right, moving into the structural geology. So these are the data that we're adding from our study to try to understand the construction of the island. Starting with this, we're going to step through the major fault zones so we can kind of understand where each of these data are coming from, and then we're going to take a closer look at the northern and then central Cordillera and some of the data that we gathered there. The northernmost fault zone is the Septentrional fault zone. Number 2 here is pointing out the Bonao-Cara fault zone. 3 is the Hatillo or Hispaniola fault zone. 4 is this fold and thrust belt just to the south of the central Cordillera. 5 is a left lateral strike slip fault, the Enriquillo Plantain Garden fault, which curves into this thrust fault here, the Bajarroco fault, that serves to uplift the Sierra de Bajarroco. So a recent work by Terrier, Sedan, and Bertil looked at seismicity and tried to classify these faults as active or potentially active. So red here is showing the active faults. These are very clearly active. You have earthquakes within our lifetimes occurring on these faults. And then the potentially active faults are faults that might have scarps that are apparent in the topography. They might have other indicators, maybe some seismicity, but whether or not it's deep seismicity or shallow seismicity or something like that, they're basically saying there might be active deformation there, and we'll provide some information into that as we get into the geomorphology section. But thinking about the structural geology, we mainly measured slicken lines, and we use slicken lines as indicators of fault kinematics or fault motion. And for those that aren't familiar, a slicken line is a striation on a fault surface. We can see some from pictures that I took in the Dominican Republic. That's formed by some topography on the opposing fault surfaces, maybe some pebbles scraping grooves into the opposing fault surface. So by measuring those, we can figure out which direction one block moved relative to the other. And these are all the data that we collected in Hispaniola. You can see we spent most of our time along the Septentrional fault. We have some data in the central Cordillera. We have some data in the south as well, but you see that there's some very convoluted patterns with the slicken lines that we measured, especially down here. Here's one example of kind of very convoluted data coming from these very small displacement faults as things are kind of wiggling around as the Earth is finding its happy position. But we'll focus on the north where we have the best kind of data set, and we can interpret these trends a bit more clearly relative to the motion of Hispaniola. So zooming in on the Septentrional fault zone, in the far east, we have mostly extensional slicken lines with a generation of strike slip slicken lines as well. So this is mostly north-south extension, and then moving across the fault, we get into more extension, more strike slip, and then ultimately, as we get further to the west into that horsetail splay, you start to get more compressional slicken lines. Looking at some of the faults that we measured, so here's Claudio along one of those normal faults measuring the slicken lines, and we'll have some stereo nets with the curvature showing the dip direction of the fault, and then these arrows are showing the directions that we measured. So there's one of those faults. Here's a pretty large normal fault phase. And just a little bit further to the west. Here's me up on a normal fault, taking some measurements. Again, we have another generation of slicken lines that are strike slip. And then here's sort of more within the Cordillera, these kind of domino style extensional features where you have the beds kind of dipping into those faults. So more or less just extension across the fault, until you get further to the west, where the fault source becomes a little bit more diffuse. And you have this feature here, which is very characteristic of transgressional deformation or oblique convergence with some component of obliquity. It's a positive flower structure. And so here's my interpretation of the outcrop here. And this is more pretty much what I'm talking about, this feature that looks like a flower and taking away the background. So this is very indicative of strike slip deformation with some component of convergence. So it's pretty clear that you're going from this extension to compression, and that's probably just related to the geometry of the boundary relative to the convergence. Looking into the central Cordillera, we have less data here just because it's super tropical, the erosion is really bad, so all your faults are kind of eroded away. In red, we have our compressional slicken lines. In purple, we have strike slip again. So again, we see these multiple generations of slicken lines, probably associated with multiple phases of deformation. Looking at the outcrop where we measured these slicken lines, in blue and shaded blue here, we have the hanging wall block moving relative to the unshaded foot wall block. And white here, we have myelinite that's been kind of exhumed and exposed later. And so if you're not familiar, myelinite is just high strain rock characterized by grain size reduction due to those high amounts of strain. So as far as the data that we measured here, like I said, we have 2 generations of slicken lines. And then from the relationships of those slicken lines, so you have some that are kind of carving into the other, you can tell which one came first. And it seems that the strike slip here came before the compression. So you have an overprint of compression onto the strike slip. This is good evidence for kind of how deformation changed within the central Cordillera as the island evolved. All right, the geomorphology of Hispaniola. Here's a nice photo of an erosional surface that I took on the northern portion of the island. It's super flat here, so this can be used as a nice datum for surface uplift. But beyond that, this is pretty much an overview picture of the geomorphology of Hispaniola and what we intend to do with the geomorphology. So what I'm showing is the topographic slope. And that is a measure of the steepness of the topography in the steepest direction from pixel to pixel. So this is a 90-meter digital elevation model. So each pixel is 90 meter by 90 meter. And so whichever way is the steepest and the amount and how steep that actually is going to be colored based on our calculations. So if it's red, it's very steep. If it's blue, it's pretty shallow. And they found that high steepness is associated with high amounts of uplift or deformation because you're going to be constantly rejuvenating the fault scar. Whereas if you stop uplift, if you stop deformation, erosion can take over and it can start to shallow the fault scar. So areas where you have high slope are areas where you likely have deformation on timescales around 1,000 up to maybe 10,000 years. So recent timescales relevant to human history. And so these areas of high slope are matching some of these potentially active areas that I showed from the Terrier, Sedan, and Bertil paper. Also some of these areas that are clearly active from historical earthquakes. In the figure on the bottom, this is coming from a swath profile from north to south across Hispaniola. And a swath profile is showing the highest and lowest elevations within this window shown by the orange lines there. So the highest, when you have a high difference between the highest and lowest elevations, means you have a lot of erosion because you have high peaks and low valleys. So you have a lot of incision kind of carving out all the material between. I've colored it by the binned KSN. This is a metric very similar to the topographic slope, except it's coming from streams. So it's the channel steepness. And when you have high channel steepness, similarly, it's going to be constantly rejuvenated by uplift, so you don't have time for erosion to shallow those streams. So it's a good indicator of where you have active deformation. So it seems that at least in the central Cordillera, most of your active deformation is concentrated in the south, likely controlled by the San Juan Los Pozos fault zone. So that seems to be steepening much of the topography in the central Cordillera. At least relative to the north and even compared to the Sierra de Nieva. All right, so this sort of becomes a complex figure, but we're going to layer different pieces on top. What we're looking at here is the elevation model. In blue, we have the local topography, which I'll get into in a bit. And then this cyan line is the drainage divide. So everything north of the drainage divide, as it sounds, is all the drainage will go that way. And everything to the south, all of the drainage will in turn go that way. The blue is the local topography. So that's the difference between the highest and the lowest elevation within a 2,000 meter kernel. And so I chose 2,000 meters just to try to bring out these features as best as possible. And then I cut everything to only above 800 meters local topography. And what we see in the Central Cordillera and the Sierra de Neva and the Sierra de Bajarroco and going into the Haitian Peninsula here is these locations of high local topography, these high relief surfaces, that's showing that this topography is out of equilibrium. The erosion and tectonics erosion can't keep pace with the tectonics. And so it's carving and you have high differences between the highest topography and the lowest topography. So varying sized valleys. But if we stack on top of this, now in yellow, these yellow dots are going to be the nick points. So this is a change in elevation, a change in slope of the stream. This can be caused by a fault. So if a fault comes up, it can change the stream from going from steep below the fault to shallow above that fault. So by putting these nick points around, we can kind of define the boundaries of this high relief surface. And then I've captured those in this 1,000 meter contour. This is the best fitting contour for these for these nick points. And so this divides the high relief portion of the Central Cordillera from the lower relief slices within the Central Cordillera that aren't really experiencing the same magnitude of deformation. Okay, and then the last bit on the geomorphology is going to be looking at the chi variable, these next two slides. So chi, for our purposes, is just a horizontal coordinate that we can use to look at the state of equilibrium of the drainage divide. So we looked at this drainage divide here in cyan going across Hispaniola, and if we want to see how that drainage will move projecting into the future, we can look at the chi across that divide. So if chi is more or less the same, the divide's not going to move. If chi has a strong contrast, so if you have high versus low chi, it's going to move in the direction of high chi. Looking at Hispaniola, we do have these strong contrasts across the main divide. So you have very high chi here, pretty low chi here. So the divide is likely moving to the southwest if we were to project into the future, and the topography overall is going to shift in that direction as you continue deformation of the Central Cordillera. So I think that's pretty cool to think about how these basins are going to evolve through time. So they're going to be eaten away because you have steeper streams coming in and taking over that divide and shifting it further to the south. Looking at chi in chi elevation space. So this is plotting the streams going across the trend of the Central Cordillera following this red arrow. This is going from east in pink to west in blue. And overall, what we see is these shallower profiles for in the west, where you have steeper profiles further to the east. And conveniently in this space, in this high elevation space, the slope of the line is the KSN. As I mentioned, that's the normalized channel steepness. So it's going to be a good proxy for uplift and deformation. So these red streams in the east have a higher KSN relative to these blue streams in the further west. But you'll notice that nested behind here on the southern portion of the drainage divide, you do have some western streams. And this is probably because that fold and thrust belt to the south of the Central Cordillera is bringing up the streams uniformly, whereas to the north, you have these faults controlling the steepness of the streams, but they more or less die out as you get further to the west. So you have active deformation on the north side of the divide. You have active deformation more concentrated in the east, whereas on the south, that fold and thrust belt is bringing up everything more or less uniformly. And then we can plot the KSN over the digital elevation model and then revisit the areas of potentially active deformation that were pointed out in this 2021 paper. And we can think about the concept of high chi, deformation, and uplift on timescales of thousands to 10,000 years maximum. So these potentially active faults, based on the elevated chi in these regions, we can likely redefine as likely active, and you do have historical seismicity there too, so that seems pretty fair. And then I've also drawn some active zones here and then added other potentially active faults based on those high KSN anomalies. So this is an example of how we can use geomorphology to think about active seismicity in neotectonics. And then the last bit of information we're going to add comes from thermocronology. For those that are familiar, what we're doing is we're using uranium, thorium, helium thermocronology, and this is based on the decay of uranium and thorium to lead. So the decay chain is shown on the right, but for example, if we think about the decay of uranium-238 to lead-206, it's going to release 8 alpha particles as that occurs. And so an alpha particle is 2 neutrons and 2 protons, and if we think back to our intro to chemistry, that's basically a helium atom. So when you hear uranium, thorium, helium, that's what we're talking about, those 2 parents going to what's produced. And so we can figure out the age based on a relationship between those parents and what's produced, because the decay of uranium to lead occurs at a known rate of about 4.5 billion years. So that's the half-life. That's how long it takes for half of that uranium to go away. And to put it a little bit more simply, we can think about the decay of uranium and thorium to lead in terms of a closure temperature. So this is really what's useful in our technique. So a closure temperature is basically when that system starts to retain those helium atoms. If it doesn't retain them, they're just going to go off into the abyss. Once the rock reaches the closure temperature, they're going to be retained. The clock starts. So the rock rises and reaches the closure temperature. Now we're retaining our helium. And then as it rises to the surface, more helium is produced. And then we know the date or the age of the rock based is proportional to the ratio of the uranium and thorium to the helium. And we're using 2 different thermochronometers here that have 2 different closure temperatures. So those are going to give us data points at different points in the crust. So apatite has a closure temperature about 70 degrees Celsius, so like 3.5 kilometers, assuming a 25 degrees C thermal gradient. And then zircon has a bit higher closure temperature, about 180 C, so even higher, like 6 or 7 kilometers. So looking at our zircon data, we'll obviously have older ages than our zircon because it's going to be higher temperature. The rocks passed through that closure temperature much longer ago than they would have passed through the apatite closure temperature. And we see pretty much two age populations. We have ages from around 20 to around maximum 38 million years. And then we have ages around 50 to 110 million years in the southern terrains of the island. And you could probably draw a line similar to the difference between the high relief and the low relief surfaces across Hispaniola between these two age populations. So you likely have a fault within the Cordillera controlling the offset of those age populations. So you have the younger ages brought up relative to those older ages. And then in the apatite ages, it's more of a mixed bag. You have ages from 3 MA to 10 MA. You have even some older ages around 26 MA. So these older ages are going to be representative of very slow exhumation relative to younger ages like 3.4 or 3.9 million years, which are marking exhumation pulse in around the late Miocene. So what we can do is we can take those apatite and zircon ages and plot them across a profile shown from A to A prime. And if we do that, we can see, we can interpret the ages from this space. So in the apatite, we see these dips in ages, which are going to be important. And in the zircon, we see that rapid drop in ages that I mentioned, likely across some fault. And what we can do is using the insights provided from numerical models, so this is from Locke and Willett 2008, we can think about how these dips in apatite ages might be related to the fold and thrust belt. So here's our thrust ramp and our thrust flat, and it's bringing up our fault propagation folds, these anticlines that are going to be bringing up younger ages over these ramps. And in the top panel here, we have distance against age. So you see those ages dipping into those anticlines across the fold and thrust belt. So we can return to our plot and try to interpret those ages based on that information. So These dips in ages are likely related to thrusts, bringing up fully to partially reset apatite grains. And so going from this very simple cross-section here, this more or less uninterpretive cross-section, we can try to interpret the internal deformation within the central Cordillera using these relationships. And so where you have white in these bars below the central Cordillera, you have unreset to partially reset ages, so meaning the older to very young ages. And those are going to be associated with major thrust faults that are exhuming all of that material or bringing that material up forth from depth. And that's happened around about 4 million years ago, just based on the ages. We also have an upper Miocene unconformity that's been deflected upwards, which serves as another data we can use to estimate the uplift of the central Cordillera. So taking that together, we can synthesize everything that we've gone over. So from the general physiography, we learned about the locations of surface uplift and subsidence. We have really high uplift in the central Cordillera. We have high uplift in the Sierra de Neva, in the southern Cordillera, that's Sierra de Bajarroco. The geology gave us clues into the evolution of tectonic setting and paleodepositional environments. So we learned about when we had plastic deposition in the basins around the central Cordillera as a way to mark when we had this transition from compression to strike slip. We had the onset, also kind of going back to that, we had the onset of continental sedimentation within those basins and it prograding out of those basins associated with that second Miocene deformational event. The structural geology gave us an idea of the fault kinematics, specifically in the northern portion of the island, how you go from extension to more compression related to the geometry of the fault. And in the central Cordillera, how you have, again, multiple phases of deformation, we can see from those cross-cutting slicken lines. The geomorphology showed us areas of recent uplift and deformation, how that might be related to potentially active faults. And then finally, we used the thermocronology to think about the exhumation of rocks and its relationship with these major tectonic events. And then we interpreted the thrust geometry within the central Cordillera based on this. So bringing this into a more graphical synthesis, we can think about how the island was constructed in the Cenozoic from each piece of information. And so this diagram has been informed by all of those pieces of data that we added to the study. So in stage one here in the Paleocene to mid-Eocene from 66 to around 41 million years ago, you had your Great Arc of the Caribbean subduction zone. So you have like a typical strain partitioning scenario you have for a subduction zone. You have your convergent deformation accommodated along the megathrust and in the accretionary prism. So that's what formerly was the Cordillera Septentrional. So you have those accretionary prism rocks that are exhumed in the Cordillera Septentrional. And then in the central Cordillera, you have strike slip deformation, maybe with some thrusting related to the convergent deformation that wasn't partitioned that fall. And these projections here are stereographic projections showing the expected structural fabric you'd have for each of those phases of deformation. So going into the late Eocene to early Miocene, this is after you have the collision or after you have the Bahama platform enter the trench and everything starts to shift around. So you go from convergent deformation in the Septentrional to more strike slip. And we saw some strike slip slicken lines there that are probably evidence of that phase of deformation. In the central Cordillera, you have the switch to compressional deformation and uplift of the central Cordillera. We know this from the onset of clastic sedimentation in the basins. We have slicken lines that record some of that convergent deformation. And then in gray here, you have the Caribbean plate, and it's starting to move towards Hispaniola along this thrust or subduction zone. And it's starting to impinge upon Hispaniola as we get into the mid to late Miocene. And so you start to have a pulse of deformation shown by red here in the central Cordillera and in the southern Cordillera, and the onset of uplift of the Sierra de Neva and the Sierra de Bajarroco. Also, you have deformation along the Enriquillo Plantain Garden Fault once you get into this time period. And again, from the geology, we know this just simply from the onset of continental deformation. So everything is uplifting related to the accretion event. We also have some slicken lines that we didn't discuss showing more or less compression along the Bajarroco fault here. And then finally, you have the time period when all the action is happening, the early Pliocene to recent. That's when we have those younger thermochronometric ages. When you're exhuming the central Cordillera and the southern terrains of Hispaniola at the highest magnitude, and you're forming that complex architecture we have within the central Cordillera. On top of this time period, I put Harvard CMT earthquake solutions showing the zones of active deformation and the style of deformation that you have in those zones. We have some compression in the northern portions of the septentrional. This is getting into the northern Hispaniola deformed belt. And then you have an extensional moment tensor along the septentrional fault. Whereas within the Muertos going into the central Cordillera, you have these kind of mixed modes of deformation in the south and these southern terrains. Again, you have mixed between compression and strike slip. And so that's pretty much all, bringing all of that together, and I'd be happy to take questions or kind of enter into a discussion for discussion.
Right, thanks, Ethan. Clearly a lot of stuff. Cool to see it come together. If anyone has any questions, whether in the room or online, if you're online, feel free to unmute yourself and shout it out.
I've got a question.
Yeah.
So if the Caribbean plate impinging on the southern part of Hispaniola is what's causing that uplift in the south,
Yeah.
and that postdates the transition between subduction and strike slip. What's driving that transition?
Between subduction and strike slip? Well, there's two options, and they can work together too if you want them to. So you have the Bahama platform, which I mentioned, may have entered the trench, and that could have kind of jammed up the trench, and you switch from subduction zone to a strike slip zone. That's the leading hypothesis for why you have the transition. The other option is looking into the mantle, where you have the Farallon plate has reached the 660 discontinuity around that time. And so you would have a pressure wave in the upper plate, which might cause the initiation of the Lesser Antilles subduction zone. And that occurs roughly at the same time. And you can tell that by restoring like the subducted plates from tomography.
Okay.
So it might be a mix of both. You have the platform enter, and then you also have this dynamic effect that might initiate the second subduction zone. But it's, yeah, I mean, we're working on that.
Yeah, I was asking because I've always thought of, Hispaniola and the other Greater Antilles kind of being like the leading edge of the Caribbean plate. But if it's a separate plate, and there's, two different convergent boundaries that are.
What do you mean?
Am I misunderstanding this completely?
What do you mean? Like,
So you mentioned like in stage 2, right, where there's the Caribbean plate is migrating northwards into the Hispaniola plate. Like kinematically, what's the
I think it'd be more helpful to go just looking at this here. Yeah, so this is what you're thinking of is when the Great Arc collided with the Bahama platform.
Okay.
And so that's when you shift subduction to the Lesser Antilles, and now you have a strike slip fault in the northern portion of the Caribbean.
All right.
Whereas Cuba is the Greater Antilles island, which is actually not, it's actually part of the North American plate.
Okay. Okay. That I swapped them. Thank you. That makes sense.
If there are no immediate questions, can you guys hear me?
First, we can't hear you.
Not my fault.
Indeed, yes.
Maybe try the volume on your computer.
Yes, hello? Hello?
Hello? Hello?
Yes.
Ask your question.
Ask your question. Did you have a question or just?
Yeah, you can't hear me. I put in the chat.
Oh, okay. But what's happening with Northwest Columbia industry? That's a great question.
I mean.
You still can hear me, huh?
Okay,
now
so
you guys-
Torsten asked what's happening with Northwest Columbia and those reconstructions. I can hear you. It's not on my side. I mean, in the last 30 million years. I know it's not what you focused. Okay. So why that northeast motion?
yeah,
Let me play this reconstruction because I admittedly just pulled the Mueller reconstruction. So yeah, it really scoots up there, huh? I'm not sure. I haven't investigated where those data come from for this reconstruction. It seems like a lot of displacement in a short amount of time, though. I would be also suspicious of that motion. But as we've seen in Colombia, we do have right lateral strike slip on the Romeral and Cauca fault. So I don't know if there's that much displacement, but there, I mean, there is evidence for some of that right lateral motion, kind of in the central and western Cordillera of Colombia. Drivers?
We can hear you if you talk.
Yeah.
Yes.
oh, why the hell am I typing then?
I don't know. I don't know. It's confusing because I can't. I'm looking at my computer. I don't see you typing.
Yeah, no. So the question is, right? I mean, this is clearly there's motion, but the timing in those reconstructions is interesting, and obviously there might be some link to the overall Caribbean dynamics, or it might be a local whatever slab effect, or it might just be made up.
Yeah, I'm guessing probably a mix of all three of those.
Yeah, but you know, it would be nice to know.
So when I was in Colombia, we looked at some of the thermochron ages there, and you have the ages line up with that kind of like Oligocene to Miocene like deformation event. So that kind of makes sense with what we're seeing here, and then also the structural geology work we did there, like we see right
Do you
lateral.
think the timing of the onset is real?
The timing, yeah, I mean, I have no idea, honestly. I haven't looked at this reconstruction closely enough. Besides,
Right, but because this is sort of where the volcanic ages indicate a change in the slab dip in the south.
yeah,
Interesting. Thanks.
What's the convergence rate happening there?
happening here.
Just like in that area.
I'm not sure. Yeah, I don't know. I'm not sure.
Like in the Caribbean.
In the Caribbean,
Yeah, like in the last couple million years.
like the northern boundary,
Like what's the speed that's going on?
relative to. It's like, I mean, in a
What's the
mantle reference
convergence
frame.
rate of the subduction, like convergence rate?
Of which there's a lot of subduction zones. I'm kind of confused. Sorry.
So you're saying like a lot of different speeds happening along there?
Along the entire
Where
Caribbean.
the Caribbean plate is moving.
Yeah, so you have around 2 centimeters of year of convergence between the North American and Caribbean plate.
Okay.
Yeah. Sorry, I mean, there's like several, like
Yeah.
Caribbean plate is more or less fixed in a mantle reference frame through time. So there's, yeah, so everything's moving around that, but at different rates, depending on where you want to look into it. Yeah, for sure.
Yeah, and all this to me like we just sort of like the plate boundary jumps in the.
Well, it's also,
The Caribbean.
Panama also really accelerates there.
Yeah.
So I think some of this is just an artifact of G plates too. Just you have to have everything, they follow this like continuously closed polygons. So everything kind of has to match up within the model. And yeah, I mean, some of that's coming from paleomag, like the locations, like the latitudinal shifts. But I don't think some displacement along these strike slip faults here are that good. I don't know.
But when you look at the volcanics, right? So there's an argument to be made that around 10 is when you have onset of general flat slab deformation. So you go from normal to flat around 9. So perhaps that's not unrelated.
Unrelated to the
No,
change.
this could actually be related to the onset of deformation.
Oh, to the late Miocene, in southern Hispaniola.
No, I'm still stuck on Colombia.
Okay.
Anyway.
I mean, I think you have strike slip there. I don't know how much displacement's on those faults though. The timing though, it makes sense from what you said, yeah. That you have the onset of flat slab, and it seems like across, like from the thermocron ages across the Caldas tear, you have a small shift, like younger ages in the flat slab portion than you have in that in the older portion, and those younger ages are kind of getting into the Miocene. So around the same time as, let's see, around the same time as when you have that kind of acceleration of motion. But we can look at that later. I have a compilation of the thermocron ages that you might be interested in looking at, that Santiago put together.
I have a general question for you. I'm sorry, from Scotia, Scotia Ridge, that Georgia has moved something like 1,800 kilometers east of South America. But a lot of argument because you don't really see what's been driving. The geology says it's happening.
Yeah.
How much control do you really have on the motion on the north side of the Caribbean? Some of that's coming out of the Cayman Trough.
Yeah. Then most of that is constrained by spreading in the Cayman Trough.
Yeah.
Do you have a spreading center like that in the Scotia, the northern section of the Scotia? Because
Not one that can move it as far as
yeah,
the geology said it move.
so yeah, I mean, in the Caribbean, it's convenient that we have all that spreading recorded. There is, I think, a difference of around 600 kilometers that's unaccounted for. Looking, I don't know if you can see in this reconstruction. Oh yeah, around here that kind of had to be subducted beneath Hispaniola to make the whole, make it palispastically work. Yeah, I think the geology says it, and then you have the spreading in the Cayman, and then you go from there.
You know, like Cuban movement, for example, how is that controlled?
Yeah, I think just paleomag, limited paleomag is the best data we have at just paleo latitudes.
I wouldn't have thought the amount of change in latitude outside the Earth.
No, it's actually not. I've compared reconstructions and found that it's really hard to say which, like, based on that argument, we can't really.
You don't have enough of 95 and 5 degrees.
Right.
You haven't done dissected variation. So.
Yeah. But we're doing some paleomag in this. Well, I'm not, but some of our collaborators are in Hispaniola just to to look at some of that as well. But again, probably with an error.
You have any GPS on that,
I'm not, no, I'm not, yeah, there's no vertical.
It's not usually definitely starting in the instance of moving all the rest of it.
yeah.
What's interesting though is if you look, Torsten has the kind of put the Caribbean in a mantle reference frame. And then if you look at that through time, the Caribbean remains relatively fixed relative to North and South America. So it's everything's more pretty much moving around the Caribbean plate rather than it being translated. It's more just sitting still and everything's moving around it.
Yeah, I mean, you can kind of see it in that movie at the end, right?
Yeah.
Like the old story about, Tim Bell and his story about garnets. The garnet when you were taking whatever else.
That's exactly right. Thanks.
Any more questions for Lisa?
We can look at this blue schist while we close it.
Cool.
Thanks, Al.
Thank you everyone for coming. Thanks Ethan again.
Thanks.
Happy thoughts.